So welcome everyone. Thanks for joining us. I'm James Ward. I'm a developer advocate at Google Cloud. And we also have with us Mark. Mark, say hi.
Hey everybody. I'm Mark Vieira, and I lead up the delivery area for the Elasticsearch engineering team at Elastic.
Glad to have you all with us today. So let's jump in. First, here's an overview of what we're going to be talking about today. In a nutshell, I'm going to talk a little bit about Google Cloud support for Gradle and how to do that and run through a demo there. And then I'll hand it over to Mark to talk about how Elastic is using Google Cloud and Gradle Enterprise. So a little bit about us. Mark, do you want to do an introduction, talk about what you do at Elastic? Or
like I said, my name is Mark, and I'm an engineer on the Elasticsearch engineering team over at Elastic. And I head up the delivery area, so we focus primarily on basically build and test and deployment infrastructure for Elasticsearch. So I'm heavily involved in CI and our CI infrastructure as well with the greater Elastic engineering team, as well as cooperating with other cross-company teams like the cloud and other product teams. So that's what I do over there.
Nice. Awesome. Yeah, and so I am a longtime Java developer and work at Google Cloud helping other Java developers or people that build on the JVM. So I do quite a bit of Kotlin and Scala as well, and just help them learn about the cloud technologies and how to deploy their apps on Google Cloud. Okay, so I want to start out just to get to know you all a little bit. And so to do that, I have a little poll, which we'll switch over to you. And so we can see really what I would like to understand from you all is how you actually run your stuff in production. Seems like a lot of people are kind of on that same path. Maybe some people are sticking with raw machines or VMs and not going to Kubernetes or Apache, and that's fine. Okay, great. Well, that's helpful for me to understand where you all are at, so that I can, as I go through some cloud stuff, hopefully connect with that. Okay, so to introduce a little bit about Google Cloud and how it relates to Gradle, I want to give a demonstration here. And what I'm going to do is I'm going to take a sample application and deploy it on Google Cloud, and this will give us a way to understand some of the machinery and pieces that are involved here. I'm up on GitHub on the Google Cloud Platform organization, and then there's these build pack samples. And we have, of course, a Gradle one. So I'm going to go to the sample Java Gradle. And down at the bottom is this button I can click, run on Google Cloud. So I'm going to click that. And this just automates some steps to take that source code and deploy it up onto Google Cloud. So I'm going to say, yes, I trust that repo, and I do want to deploy it. This is going to take me into something called Cloud Shell, which is like SSH in the cloud. And so we see this text-based console. It's now asking me, hey, are you sure you want to authorize this thing to make Google Cloud API calls on your behalf? And I trust it, so I'm going to say authorize. The first thing that happened was it cloned the Git repo that we were just looking at down to my Cloud Shell instance. And then in Google Cloud, everything is organized into projects. And a project is really like a folder of a bunch of resources on Google Cloud. And I only have one project in this particular user account, which is JW Demo. So I'm going to say, yep, use the JW Demo project. And then it says, all right, which region do you want to deploy this application in? Regions are multi-data centers. So there's data centers that are then organized into regions. So how I'm going to be deploying this today on something called Cloud Run, I specify the region, and then Cloud Run automatically does the balancing and failover and all that kind of stuff across the actual availability zones underneath that. So I'm going to use the US Central region. And now we get into the actual build part. So I've got some source code, and I need to turn that into a Docker container image. There's a number of different ways that we can do that. Traditional way is with Docker files, but I'm using something called build packs. And build packs are part of the Cloud Native Computing Foundation, and they're just a standard way to transform source code into container images. And in this case, I'm using the Google Cloud build packs. We'll take a look at those in a little bit, but that's what this builder parameter here is doing is telling it to use the Google Cloud Build Packs. Let me go show you the source code for what we're actually running. So of course I have my build.gradle file, and you'll see that there's really nothing special here in this Gradle build about how to containerize this application. It's just a standard build, no information about the actual containerization. And I'll show you the source code just so you can see that sure enough, there is a server here. It's just a basic HTTP server in Java, and it's just going to respond and say hello world. So that's my Java code. So what's happening with build packs is it is detecting, oh, this is a Gradle project, and I know how to build a Gradle project. And the output of that whole process is actually hidden from us. We don't see all of the downloading Gradle, using Gradle wrapper. We don't see it downloading the dependencies, downloading, it actually doesn't have to download Java because that's actually in the container, but then actually running the Gradle build and then taking the jar files that are outputted from that and assembling them into layers within my Docker container. So we don't see any of that in Cloud Shell in the way that we ran this, but that's actually what happened. And if you run that pack build command on your own, then you'll see the full output there. Okay, so what happened when we ran that pack build command using build packs, it transformed that source code into a container image, and it stored that container image up on the Google Container Registry at this URL. So the gcr.io is the Google Container Registry, then it stores it in my project, and then it gives it a name, the sample Java Gradle. So after it built that with build packs, it stored it in the local Docker daemon, which is local inside of Cloud Shell. And then I needed to push that up. So I did a Docker push to push that up to the container registry. And now that it's in the container registry, now I can deploy it. And so that script automatically did this gcloud run deploy, which is using this cloud run service, which takes container images as the artifact that it deploys up in the cloud. And you can see it specified the image to use as being that one that was created there. And so great, now it's all deployed. It allows unauthenticated requests. And now I can go open this app in my browser, and it's now making an HTTP request to that container, and it will scale up, scale down, all that kind of stuff, serverless. So I don't have to think about scaling, it does it all automatically for me. Okay, so that was just 3 steps that were automated for me to go from source code to a container to that container running in Cloud Run. We can open up this console here where we can go see the details of this particular service, see the settings, deploy new revisions, set up CI, all that kind of stuff, all within this console. But what I want to show you is over in the container registry. What we can do is we can go find that that sample that I just built. And I've got a lot of samples, but that was a sample Java Gradle one. And we can see the container images that were created. You'll see that this one was created 2 minutes ago. And so that's the container image with the latest tag that was created, which we saw inside of Cloud Shell. So now that I've got a container image, of course, I can deploy that to and run that wherever you want to run containers. I could pull that down to my local machine, run it with Docker locally. You can see the deploy to Cloud Run, which we already did. You can see the deploy to Kubernetes, the Google Kubernetes engine, or we can also deploy that just to a raw VM in the cloud, which on Google Cloud is a Google compute engine, is the raw compute instances. So just a standard container image, and you can run that wherever you want to run your container images. Okay, so that is how we can take applications that are built with Gradle and run them in the compute side of Google Cloud. There's, of course, lots of other parts of Google Cloud. There's AI services. There's all sorts of different data stores and messaging and lots of different pieces to Google Cloud. But specifically to Gradle, I wanted to show you how we use containers and containerization to deploy those on the compute side of Google Cloud. If you want to learn more about the build packs for Google Cloud, with build packs, there are a number of different implementations of build packs that you can use. You can use Heroku's build packs. You can use Packeto's build packs. What I'm using is the Google Cloud build packs, which have support for Java with Maven and Gradle and a bunch of other languages as well. Okay. So I wanted to run through that quick little introduction just so you can see the basics of Google Cloud and how you can use Gradle builds to produce and then use build packs or whatever else you want to go from that source code with a Gradle build to a container image and then run that on Google Cloud. So that's your quick little introduction to Google Cloud. Now we're going to talk, I'm going to hand it over to Mark, and we're going to learn about how Elastic uses Google Cloud specifically for the CI pieces with Gradle Enterprise. So, and I think Mark's going to kick us off with a poll. So let's go to the poll, and Mark, take it away.
Awesome. Thanks, James. Yeah, it looks like the majority of you are using static workers. So what I'm going to talk about might be interesting to you. For the folks that are using dynamic workers, you might get some tips as well. For containers, containers are really just kind of another type of dynamic workers in a way. So those two are kind of the principles we're going to talk about sort of apply to both. So yeah, just a little bit about the team I work on at Elastic. So I'm on the delivery team for the Elasticsearch engineering team, which is obviously primarily responsible for delivering new features for Elasticsearch. And we're about 70 or so developers. In terms of the scale of our build, which is basically all Java. It takes an hour and a half to 2 hours if you were to just run the whole test suite locally, the whole set of integration tests that we have and backwards compatibility tests. It's actually considerably more than that when we think, we then subsequently run that test suite against every compatible version of Elastic that the current development branch is compatible with, and on every operating system that we support and every Java version that we run. So the build matrix is quite large, and so we end up running many builds, and so part of that is what we're gonna talk about. So at Elastic, we run exclusively all of our CI workers basically on Google Cloud, and there's a number of benefits to this, right? Basically scalability is really flexible in terms of both how many agents do I need, right? And I'm running 10 or 100 or 1,000 concurrent builds, and also in terms of basically the configuration of those builds, right? So I might have certain tasks that run in CI that have different types of workloads, right? So some may be more CPU bound, others more IO bound, other more memory bound. So my jobs so the agents that my jobs run on can be tailored in that regard to get sort of the most bang for the buck. And also we can make those build agents ephemeral, right? Which is basically we spin up a machine, it's completely clean, just preloaded with whatever we want on it. So we do things like when we build our images, we preload it with dependencies and whatnot. And then after my build runs, we just throw that thing away. We never use it again. And that's really useful for things like weeding out oddness in build failures where maybe there was some stale stuff that was left around. And also we have tests that are just kind of difficult to clean up after. So things like tests that involve installing services and installing RPM and Debian packages, right? They actually modify the underlying machine that they're running on. And so it's nice to be able to run those test suites and then just toss that box away and get another one for the next build. So as I mentioned, at Elastic, we run all of our CI jobs on dynamically allocated ephemeral workers on Google Compute Engine. So essentially, I trigger a job, the job goes in the queue. We pull the queue to see, someone's waiting for a job, and then the job has various metadata on it. Let's say I want a Linux machine, a Red Hat 8 Linux machine with Docker installed on it. And then we will spawn a worker that meets that criteria. We have a various series of Packer jobs that build very specific images. Like I said, Elasticsearch is in addition to being a cloud operated provider, it's also an on-premises offering. So we have to support a number of different, basically, deployment environments, right? So whether you run it on Windows or Linux, or what version of Linux, or with what JVM, et cetera, with encrypted volumes and FIPS enabled and all these different scenarios. So we pre-build a bunch of images that mimic a particular supported deployment environment. And then when we kick off a job, we spin up that image and execute the integration test suite on that machine. So we have pretty strict requirements on how we want to run, and many other applications might be similar. So for us, sort of building on raw VMs, so to speak, instead of containers, is kind of a strict requirement, because we want really strict control over what the underlying system that Elasticsearch is running in that test environment, because that's part of what we're testing in a way. And our engineering infrastructure team built a custom tool for this that they call Go Build, and that's what actually orchestrates all these workers. So it's periodically pulling the Jenkins server and getting the current queue, and then spinning up workers that match the requirements for each of the queued jobs dynamically. And what I've included in this slide is basically, some data over a couple day period on the number of workers. Each color band here is basically a different team within Elasticsearch, or within Elastic rather. So Elasticsearch, Kibana, APM security, all the different products at Elastic, and then how many basically dynamic workers have been allocated at any one time. And you can see it's very spiky. It kind of follows time zones and working, right? So one of the big benefits of doing this stuff dynamically is that, if we only have 50 jobs running, we only have 50 workers running. And if we have 1,000 jobs running, then we can have 1,000 workers running. So it's, we get kind of the both benefits. We have this sort of almost infinite scale effectively on how big our CI can go, but we're not sort of paying for resources that aren't being used. As soon as that job finishes, the agent that it was running on can get shut down. So we can really effectively, use the resources at hand. So yeah, what do we do CI for in general, right? So in the end, the point of CI is for a developer to get an answer about changes that they've made, right? So I make some changes. Again, we have a 90-minute, 2-hour-long test suite. I'm not going to make some changes and then kick off the build on my local machine and then go out to lunch. Well, maybe I'll go snowboarding or something and then come back in an hour. But ideally, we want to get feedback to the developers as quickly as possible. Say yes, the changes you made are compatible and meet all the assertions and quality gates. And so typically this is done via pull requests and stuff like that. And then also once these things get merged, you want to make sure that the mainline branch is all good. And we want to ensure that if I merge something, that I'm not getting a notification 2 hours later that I broke something, and I might long be gone or it's the weekend by that point, right? So we want to get feedback to developers as quickly as possible. And really the two sort of knobs we have to turn to shorten that feedback cycle are, we either have the checks do less stuff, right? We just make the checks more efficient, right? And this is things like build avoidance and test avoidance. So using the Gradle build cache, things like that, and up-to-date checks to basically detect, hey, these changes don't affect the outcome of these tests, so we don't have to run them, things like that. And then obviously you can just make your tests more efficient, right? So you can optimize the way they can run. But to some degree, the do less work thing, you're going to sort of kind of get diminishing returns to some extent, right? In the end, some code changes are going to require vast amounts of testing, right? So if I test something in a very core dependency up at the top of my dependency tree, there's really no way to avoid running all the downstream tests, right? We just have to do it. So how do we shorten the feedback cycle in those sort of non-optimal scenarios? And really the option is to do more of that work in parallel, right? So we'll talk a little bit more about what that looks like. So when we talk about parallelizing builds, there's really two ways to do it, right? We can parallelize builds either vertically or horizontally. And for the purposes of this, when I say vertically, in this context, I mean basically making my build agent larger, right? Throwing more CPU cores at it, increasing the number of max workers in my Gradle build, so I run more tests on a single machine in parallel. And then horizontally scaling in this context means basically more CI jobs, running more builds in parallel in CI. So instead of kicking off one mega job that runs the whole test suite on some giant VM, I'll kick off a number of smaller jobs that run a portion of the test suite in parallel, and then perhaps at the end we'll aggregate, those results and send them to the developer or the person that's interested in them. And so there's kind of trade-offs with each of these, right? Vertical scaling is just frankly easier, right? It's just like, well, just give more CPU cores to the build agent, crank up the workers, and you're basically done at that point, right? Assuming that your build scales. So it's pretty easy to just do that, just throw more cores basically at the problem. There's also a lot less overhead, right? So by just making the one job larger, I'm spinning up a single agent. I'm doing only a single checkout. If I have to download any dependencies, I only have to do that one time, right? So the overhead of creating jobs and allocating workers and doing that is non-zero, right? So the more times you do that, you're sort of adding that overhead. So vertically scaling to a degree sort of is more efficient until you start hitting certain scalability walls. But vertical scaling has diminishing returns, right? Depending on your project, there just may be certain architectural bottlenecks in it, right? It's like, well, we can't run these tests until we've built this thing, and that takes a while. And so just after a while, you'll kind of see this thing where for any given build, after a certain number of workers, you just stop getting benefit from it for any number of reasons. Either there's just not enough parallel test suites to run. There could be things where the tests start to get bound by other resources on the machine. So like, for example, like IO, things like that. So there's always going to be kind of a sweet spot that you'll eventually hit. And then you kind of won't be able to get any more gains by just throwing more resources at a single job. So for horizontal scaling, right, the benefit is that I just mentioned, we can scale that much farther, right? So we can make any number of jobs parallel, right? And because we're doing that, we're doing less work on that machine, we can make the workers potentially smaller, right? And a little bit more efficient. The idea is that the worker is at max capacity, right, throughout as much of the build as possible. And that kind of, talking about that, when we talk about parallelizing builds and then being sort of non-optimal, this is kind of what I'm talking about, right? So here's an example of a build that's running on a machine with lots of workers, but because of the nature of the way that test suites are running, there's only a handful of them that we can run in parallel. So you end up getting this, this execution graph that looks like this, right? So we monitor this stuff with Gradle Enterprise by every single one of our builds creates Build Scan and send it to Gradle Enterprise, and we use that data to determine how well we're doing. So in this Build Scan, which is a captured snapshot of what happened during this build, we can easily see here's the task execution plan for this build, and you can see while there's 16 or so workers, only 4 or 5 of them are actually busy at any one time because of the nature of the build. And if we go and look at the resource utilization on this machine at the same time, you'll see it only even peaks at 50%, and it's probably rarely above 30. So we're really over provisioning this build agent, right? We really could, for this job, probably run this job on a much smaller worker, right? And obviously there's costs associated with that. So when we consider horizontal scaling, the biggest thing is we have to kind of maybe account for that overhead, right? So for example, if I'm going to run my integration test suite, typically to do so, my build is going to have to first construct all the artifacts necessary to execute the test, right? So it's going to have to compile all my production code, assemble, whatever my artifact is. So in case of Elasticsearch, right, it actually builds in a full Elasticsearch distribution, has to compile the tests themselves. And then finally, the tests get executed against the production code. And depending on your project, that overhead of building basically the test artifact that you're going to validate can be significant, right? I mean, it could be 30 seconds, but it could be minutes or something to build that artifact. So what ends up happening is the more parallel builds you have, for each one of those, you're adding that build overhead time, right? So for each job, each one of them has to do this sort of redundant work of building the stuff it needs to test, right? And that's obviously not ideal. In the end, the feedback times will probably be reduced, right? The total time to get an answer to your developer, but the sort of cumulative time of the builds will be potentially larger than if it ran on a single worker, right? So we're sort of balancing these two goals, right? It's like we want to give developers an answer as quickly as possible, but we also want to leverage our resources as efficiently as possible, right? Because again, in this scenario, we're running dynamic workers. So for every minute that worker's running, that's cost. And so for every minute that we reduce, we can save infrastructure costs, right? And we want to do that whenever possible. So in the top part here, when you kind of see this non-optimal, scenario, right, where this compile step we're doing over and over for each one of these jobs, and even though we're compiling the same code for each of these tests, it's just the tests that we're executing that are different, right? So what we've leveraged is, in our Gradle Enterprise deployment, it's included a build cache, right? So the intention there is that we sort of set our build pipeline up in stages, right? So where we have an initial stage that builds everything, so compiles and builds the artifacts, and then the results of that get pushed to the remote Gradle build cache. And then all the downstream builds will then reuse that artifact from the upstream cache. So now that compile step for each of those subsequent jobs is basically a no-op. It's just saying, hey, has somebody already built this? Yep, cool, I'll fetch it from the cache, and then I'm done, right? And so by doing that, and by being sort of a little bit more intelligent and conscious about how you sort of structure the topography of your build jobs in your pipeline, you can essentially minimize that overhead, right? So in the end, you're still doing the same amount of work, right? The end-to-end time is kind of the same, but you're reducing that sort of redundant work that you're doing in each of those jobs. And there's also other sort of benefits too, right? In scenarios where you have to sort of re-trigger these jobs, right? Again, you can still reuse those cache artifacts and get that time down. So that's super helpful for us to have been able to leverage the build cache to basically not have to redo all this work over and over. And in this scenario, maybe it's 3 jobs, but it could be 50. So if you think 50 jobs times it takes a minute to build your code, that's nearly an hour of sort of cumulative build time that you've saved off that pipeline, right? So it adds up quite quickly. So yeah, that's kind of what I wanted to talk about. We've come to the end of the material that James and I wanted to go over with you all. So I hope that was kind of helpful. So I'm give everyone an opportunity to kind of look at this slide. Here's some more sort of resources that you can look at if you're more interested in some of this information. So the folks at Gradle provide a series of videos about these sort of similar topics, how to sort of efficiently leverage CI resources in the cloud. As well, you can take a look at getting a free trial for Gradle Enterprise. Like I mentioned, we leverage Gradle Enterprise instance at Elastic that's used by several of our teams, and that's really critical to some of the work we do. So if you want to take a look at how you might leverage that at your organization, you can do that. And also, go over to the Google Cloud GitHub repo and take a look at some of the samples that James showed off there, which is really neat. So I think at this point we'll open it up to questions.
And I've got a question for you, Mark. So you talked a little bit about how you pick the GCE instance size based on you see the chart of CPU utilization as an example. If that's at 100%, do you say, okay, we need to go from an 8 CPU to a 16 CPU or whatever? How do you make the decision on how you size the machine type to the job?
Yeah, so the other thing is that it may not be that we necessarily want to increase the size of the agent. We may want to decrease what we're asking it to do, right? So the other part of it may be reducing the number of workers on the build side, because that may not. Because again, if depending on what the bottleneck might be, just bumping that up may not necessarily be the thing we want to do. And so we do that a lot of places where sort of depending on the nature we're running, we'll sort of determine a number of workers. So for example, we have builds, some of our builds run in RAM because a lot of our tests are very, very IO bound. So we just run the whole build in a RAM disk. So we'll have an agent that maybe not super CPU, but it has a ton of RAM because we use the whole build workspace will run in memory. And then other builds will say, oh, are we running on a RAM disk? Okay, if not, let's throttle down the number of workers so we don't, cause the machine to crumble, essentially. So you'll see weird things like that too, where you'll look at the chart and it's only at 30% CPU, yet tests are timing out, right? It's well, there's this other resource that's actually constrained. So it's definitely it gets
a bit tricky to decide all right, you've got all these different knobs to turn. Some of those knobs are how much you want the thing to do. Some are how much CPU you want this thing to have, how much RAM you want it to have. And then I guess another one may be do you want this to run on SSDs or non-SSDs? And so it seems like there's not a lot of knobs. But with Gradle Enterprise, you're able to get some insight into where your bottlenecks potentially are, and then you can decide how to twist those knobs depending on that.
Exactly.
Cool. Okay, first question was, for node builds, the humongous node modules means that using local NPM cache on the build server reduces NPM install time from 20 minutes to 2 minutes. So if the server instance is new every time, would this mean that we will see always slow builds for node builds?
So that's a really good question. So that's not specific to Node. NPM is sort of the worst offender in many in this case, because many node modules directories are gigabytes in size. Yes. So one of, and I may have very briefly mentioned it. So we, the images that we spin up for our GCE workers are custom built by our infrastructure team with Packer. And part of the Packer build process, it's installing the JDKs and stuff like that, right? It's installing all the sort of dependencies that we need on the machine. And then there's another step that actually seeds it with all the dependencies for the project that's intended to be built for it. So in the case of Kibana, which is a Node app, right? They run npm install to first populate that node modules directory on the actual image that it gets built in. And similarly for Elasticsearch, we do the same thing. We resolve all the dependencies that we'll need. So we populate, download all the jars we need and get them in the Gradle cache. We'll do a Docker pool on any Docker images that we might use as part of our build, stuff like that. So all that stuff is going to be on the agent.
On the VM.
99% of it, unless someone bumped a dependency in between when the image was built and the build ran, is going to be already on the image when it spawns. So we sort of seed the agents with those images so that we avoid that overhead, because it is significant.
And then do you have some automated process that says, all right, for Kibana, the package.json changed and now we need to kick off a rebuild of the base VM image or something? Or is that all manual? Yeah,
it's not that up to speed. We basically run them nightly, right? So it's any dependencies that changed in the last 24 hours will have to be re-downloaded, but it's usually such a small amount, right? So every night we'll update.
It's not a lot of
images
in particular,
and if no dependencies have changed, then it doesn't do anything. And if a couple of dependencies have changed, it'll download, a few megabytes of stuff, right? But,
yeah, cool. Well, thanks, Prashant, for the question. Hopefully that was helpful. Okay, question here from Nate. How do you recommend this for a multi-language environment, Go, Python, etc.? Dynamic languages may just be testing and packaging. And it looks like this is maybe about build packs. It says, but do build packs and Gradle Enterprise work in this case? Do you use labels to just avoid non-Java builds? So there are build packs. If this question is specific to build packs, there are build packs for all sorts of different languages. One of the nice things about build packs is that you run build packs on source code, and then it detects, oh, do I need to do a Go build for this? Do I need to do a Python build for this? Do I need to do a Java Gradle build for this? So the build packs will detect that, and then the build pack has knowledge about how to build that particular technology. So it's going to do the right thing, for Go and for Python and Java, whatever. And then there was a question about Gradle Enterprise and build packs together. And so the build packs is really just about creating the container image. I'm sure that you can configure build packs to be able to have the configuration information for Gradle Enterprise in them. And so because that's just built into Gradle. And so yeah, that's certainly possible. Typically, environment variables are the way to bind configuration into the build pack process. So if you have some Gradle Enterprise key that you need to pass into the build pack, then you do that through an environment variable. So I think all those things could be combined. Nate, hopefully that was what you were asking about. But Mark, did you have any other thoughts on that? Okay.
Just a little bit. So our cloud team, which also leverages Gradle Enterprise, is also a polyglot environment. And one of the things that they do is, with microservices and all that stuff, right? They actually push entire Docker images into the Gradle build cache. So they'll do a build that builds 50 services, and the code change only changed one of them. So they'll actually pull down the other however many Docker images from the cache itself. So they sort of cache it at very granular level.
Nice. Yeah, build packs actually uses a Docker daemon as its cache. And so what would be interesting, I don't know if anybody's explored this, but with build packs specifically, would they be faster with using the Gradle build cache for the Docker containers? That'd be interesting to explore. Okay, let's see. Question from Francisco. Are you basically putting into practice the recent Gradle distributed cache and testing suite? I think that's a question from Mark.
So yeah, we use the distributed cache heavily, right? So all of our developers are hitting it and things like that. The distributed testing, we're looking into using that. We have some sort of unique testing requirements for Elasticsearch make the distributed testing tricky. But essentially what our tests do is they sort of spin up an Elasticsearch cluster that might be, half a dozen nodes all certain way, and then sort of slam it with a test suite. And that becomes tricky to figure out how to distribute that in a way that's sort of dynamic and intelligent. And so we're more relying on basically CI to be that distributed worker suite for us. So instead of a developer will instead just create a pull request and let CI do all the testing in and get the feedback back.
Interesting. There's a question from Roberto. First, he said, great talk. Hey, thanks, Roberto. And then he had a question for you, Mark, but it actually is a question about distributed testing. So I think you.
Yeah, I think that my previous answer applies there. For similar reasons, right? So we're not really leveraging distributing testing at this time. We want to. Ideally, what we would do is we would sort of move the orchestration of setting up that cluster for integration testing into the tests themselves so that we could leverage that feature. And that would actually give us a lot of other benefits as well. So things like being able to more easily execute tests from the IDE and stuff like that. But that's an effort that is underway.
Cool. Okay, a question from Shannon for you, Mark. Shannon says, any reason behind Go Build versus using the Jenkins Cloud plugin?
That is a good question, and I don't have a good answer for you. Mainly because this is infrastructure that's managed by the engineering infrastructure team. I suspect there were reasons for sort of rolling the own solution out there. There's maybe some flexibility with the Jenkins Cloud plugin that maybe wasn't available at the time that they developed Go Build. I don't have specific reasons why.
So it sounds like the Jenkins Cloud plugin, which I'm not familiar with, but it's doing something similar to Go Build, where it's dynamically creating instances for you as you need more, a larger pool of agents.
Yeah, I suspect if that works for you, then you should just use that.
Yeah, and Go Build is not open source, is that right?
It is not.
Okay. Cool. So sounds like Jenkins Cloud would be a great option, and hopefully it works with Google Cloud and the Google Compute Engine. I would guess that it does. All right. Well, let us know if you have any other questions. Let's see. Oh, a question from Prashant. Could you please show again how the Cloud Run deploy was initiated from the GitHub repo? Because Prashant unfortunately missed that part. So if you go into the github.com Google Cloud Platform and then build pack-samples, and then there's a Gradle example in there if you want to use the Gradle one. If you click on that, in the README for that, down at the bottom of the page, you'll see a button that is deploy on Google Cloud. And I just clicked that button, and that was how I walked through the process, which is really just automating some steps that you can do manually or you could do through your CI system. It was automating using pack build to create the container image from that source code, and then doing the Docker push to push it to the Google Container Registry, and then doing gcloud run deploy, which is the command line to deploy a container image to Cloud Run. Of course, once you get a container image, you can run that wherever you want to run your containers. But that particular button does just the automation of those 3 steps for you. So thanks, Prashant. Give it a try and let me know how it goes. Okay, Andre had a question about, are you using the Gradle daemon in your pipeline? That's a good question for Mark. For me, I actually turn off the Gradle daemon in my CI builds just because it's not needed. I'm not running multiple kind of Gradle processes that would take advantage of the Gradle daemon. So I actually turn it off for my CI builds, but maybe Mark does something different.
Yeah, so the daemon being enabled is the default. If you are using ephemeral workers, you might say, well, what's the point of running the daemon? Because again, I'm not going to run another subsequent build using that daemon, and it's just going to get overused. I mean, so there's a few things. One is, if you are modifying the JVM arguments in any way, shape, or form, you're already using the daemon, right? So even if you're not actually using the daemon, you're still using the daemon because Gradle has to fork a new process with those, like that heap settings that you used, and then it just throws it away at the end, which is the same as just using the daemon and then throwing away the machine at the end.
I think so. When you actually tell Gradle to not use the daemon, it actually uses the daemon, but then just stops it after the build is done.
Correct.
So the daemon is still underneath the code.
It's what's called a single-use daemon that just like didn't. Okay, so whatever overhead you might be concerned about, that like having another process run, is still sort of there in a sense. It's just kind of hidden for some abstraction. So. Yeah. The other thing is, like, we do use the daemon because we sort of run nested builds in our build. So for example, we'll build the main branch, and then we'll build an in development branch that we're doing compatibility testing in a sort of nested build. And we do that several times in a single build. And there is the possibility of daemons being reused when in those nested builds. So there's technically multiple builds per job. But in general, my recommendation is just use the daemon, just use the defaults. There's really no, there are some optimizations of the daemon in some cases, and there's really very little overhead. So I would just generally recommend go with the defaults and leave it there.
Easy. Okay. Another question from Shannon. Are workers only used for a single job, or is there some reuse of the workers across jobs?
Yeah, all workers are only ever used for one job. There are some very unique exceptions to that use case. Very specific sorts of like metal workers used for performance testing and things like that. But 99.9% of our jobs run on a single worker, and then it's tossed away. We do, though, however, have mechanisms to basically keep it alive. So we can go in Jenkins and say, hey, when this build is done, don't shut down the worker because I want to go peek at what's going on. If we're having test failures that we want to investigate, we may want to actually go on the machine and look on disk and see what happened, what went on. So at least having the ability to keep the ephemeral workers around after the job, but not running any subsequent jobs on it, but just not immediately destroy it, so that you can do some debugging is sort of a key capability you want to have.
Nice. Question just came in from Duran, who asks, are you running nested builds using a Gradle build type of task? And if so, how do you get build scans from those nested builds?
Good question. No, we don't. So the Gradle build task is this sort of Frankenstein monster of like running a build, but it doesn't actually run in a forked VM. It's kind of weird. So in general, I think that task might even be deprecated. It might even be getting removed in Gradle 7.0. So we actually just use an exec task to just shell out to the wrapper and run it like that, and then just sort of consume that output. It does produce a build scan, and we actually tag the build scans as being nested, so that when you have a build that has 10 build scans in it, you can kind of ignore the ones you don't care about. So basically, we use the Gradle build scan plugin for Jenkins, and if you go to a Jenkins job, you'll see there'll be however many build scans in there, one for each build that occurred during the job. Usually, the last build scan is the sort of outer job, and then all the previous ones are all the nested builds. And so you can kind of filter them out that way. So we tag them in build scans so we can sort of filter out the nested builds, which don't run tests, they just build artifacts.
Nice. Yeah, so that totally makes sense on why the Gradle daemon in that case would have a benefit as well. So, all right. Well, thanks so much, Mark, for sharing your wisdom with us, and hopefully that was useful for everyone. And thanks for joining us. Have a great day.